Okay, let's get started. Sorry for the delay. I'm having some technical difficulties with my computer. Assignment number 5 is due on November 11th at noon. We will continue with the R regression section today. Are there any questions before we get started? Okay. So we left off last time on about page 9 of the notes. We were talking about how to use the plot function to construct a scatter plot. And just to review here, inside the plot function itself, there's an x argument and y argument, and that's where you put what's going to be on the x-axis and what's going to be on the y-axis. Our data that we're working with is the GPA data set, and so to access the x-axis variable, we say GPA $HS.GPA. So that dollar sign allows us to extract a certain component of that data frame called GPA. And we do a similar thing to get the college GPAs out. Then we have a number of different optional arguments, and most of these argument names are self-explanatory, such as xlab means x-axis label. In particular, we saw COL correspond to the color that we want for the plotting points. Now, on the bottom page 9, I start talking about some more specifics regarding these arguments. So, for example, with respect to those colors, if you want to see all the colors that are available to you, at least by default in R, we can issue a command prompt the colors function, and that will print off 657 different colors, ranging from obvious ones such as yellow to maybe not as obvious ones such as thistle 4. I'm sure that thistle 4 is so much prettier than thistle 1. But anyway, those are the color names that you have access to. You can also specify RGB or other color formation equivalents too. I never have had to do that in the past. I just simply use like red, blue, black. Or I come to this colors function, extract a particular color name that I like. However, if you are really into colors, there is a link on my website that will lead you to here that shows all 657 colors by their number so that you can see what's available to you. You can actually even specify, well, I won't get into that. Never mind. So anyway, so those are the colors. Now, with respect to PCH, remember that's plotting character, and there are 24 different plotting characters that are available to you by default. I believe you can have more plotting characters available to you. I've never have had the need for it, so I don't know exactly how to do that, to be honest, but I believe you can. So plotting character number 1 corresponds to this open circle, and open circles are often very good plotting characters because it allows you to, if you have a little bit of overlap between two different points that are on a plot, this will still allow you to see both points unless the exact values of what's being plotted are exactly the same. And so you can see the various plotting characters that are available to you there. Now, if you remember, we also looked at this panel.first argument last time. And that basically just specifies, okay, what do you want plotted on the plot first before you plot any points? And I chose to use the function R called grid. Grid gives me grid lines. So if I wanted to, I could actually execute this code without the panel.first part there. And then right after it, I could issue the command grid and then the corresponding options there. And I still will get grid lines. It's just that those grid lines will be drawn on top of the plotting points instead of behind the plotting points. points as you would normally expect. It's a minor thing, but still it makes your plot look prettier. So the color of those grid lines, if you remember, was gray. The default is actually light gray, and that generally works fine too. And then LTY stands for line type. I wanted a dotted line. And there's a variety of different line types that you have available to you. So you can specify them simply by name, solid, dash, dotted, or you can specify them by their corresponding number. There are 6 different line types that are given to you by default. But as my next bullet shows, and I'd like you to read that on your own, you basically have access to an infinite number of line types in the end. Now, there are a number of different default options for any graphic that you make. And these default options are controlled by the function called par. So, for example, here. So you might remember in my code, I specified I want my x-axis limits to be between 0 and, it might be there, 4.5. Okay? But notice how R actually went a little bit further. Well, the default for how R does these plots, even when you specify certain x-axis limits, is to go 4% farther out on both sides. That's the default. Now, how can you change that to maybe you want it actually at 0 and you want it actually at 4.5 in terms of the far limits of that x-axis? That's where the par function, which controls these graphical defaults, can help you. So to see more information about the par function, what do you think you should do? Well, type help, parentheses, par, end parentheses. Or you can access it through more point-and-click methods, as we showed before. And so here's the par function. And I'm going to find, because I know where to look, just at the same time, I'm going to go to the x8xs argument for par. This controls that x-axis there. And if you notice, in terms of the style, it does. Style R is actually the default. So notice this is actually listed first. That means this is the default. R stands for regular. It extends the data range by 4% at each end. So if I want to change this to it at the exact limits I specify, I can use I. Just to illustrate how that would work, let me come over here. Now, my technical difficulties I was having before I started class here was with respect to my using tin. I won't get into the details of what was the problem. I don't think it's really worth our time. So there's my plot. And let's say, though, that I want to control that x-axis more finely. So I can do par x8xs equal, quote, I, end quote. And then run that same plot code again. And notice what happened to my x-axis. It is actually starting exactly where I've specified. It ends exactly where I specified. Now I'm just going to change this back, though. So that option, or that change in that option of how the x-axis reacts is going to remain that way until you close R. And since I want to do some more plots later on in class, I'm going to change back to the default. Par is a very useful function. And we will look at par probably a little bit more today. But for you to really have a full understanding of what par allows you to do, take a look at the help for it. It has lots and lots and lots of different arguments with it. Okay. Well, let's say that you got this plot now, and for some reason, you want to actually bring this plot into a Word document. So that maybe if you're doing a report or a homework assignment, maybe for another class, and you want it to work in Word for some reason, we can come over here to, we'll make sure that this plot is actually active. I come over here to File, Copy to the Clipboard as a meta file. Open up Word. And I can paste it into Word. Now, starting with Word 2013, a really odd thing happens is that notice when I highlight this whole plot, notice how much empty space is actually around it. I really don't know why that happened. This wasn't in any other version of Word before. And so, in the end, it's not a big deal. It's more just a kind of a hassle. Just crop around it to make it look a little bit nicer. Okay? And so now you have a more compact area around it. Now, also, you can save a particular, you can save your graphics file too. Just click on File, Save As, and you have a whole bunch of different options, such as JPEG, a PNG file. The best rendering of the plot in terms of what will make it look best in documents is if you did PDF or PostScript. So I can just click on PDF, and I can save it out. Okay? Now, sometimes, though, especially if you have a lot of plots that you want to do that with, it might be just easier just to use code. And so what I've done here is I've provided the code of how you can actually save a graph out as a PDF file. And simply use the PDF function. You have some arguments. Once you've issued that function, then any kind of graphics will go to a PDF file that you have specified as here with figure-temp.pdf. The size is 6 inches by 6 inches. So if I kept on making plots, they would go in that file. To tell R to stop putting stuff in there and to put stuff back into your graphics window, because this isn't going to go to the graphics window because it's going to go to the PDF, do dev.off, which means device off. So turn off going to the PDF. So that's how you can get a PDF out using code. For my analysis categorical data book, I had to do that for every single plot that I generated. Now, there are going to be times where you would like to have finer control of, let's say, the tick marks that appear on X or Y axes. So, for example, here in this plot, you can see that instead of being 0, 0.5, 1, I'm sorry, instead of being 0, 1, 2, 3, and 4, as in the previous plot, now my major tick marks, meaning where I actually draw a number or label a number, or label it with a number, now it's 0, 0.5, 1, 1.5 in this plot. Also, I have minor tick marks as well. These are the little things that are in between, and kind of help you a little bit see, or make judgments about a point that falls in between. Well, how can you get R then to make these changes from the default? Well, this is how. Let me get my code. Okay, so I issued exactly the same code as before, except for I added this particular argument there. XAXT stands for X-axis tick marks, and I used the argument value of N for no. Don't draw anything. And so now I have a plot that you have no idea about the scale, what's on the X-axis. To put down the scale on that X-axis, that's where we can work with the function axis. So, axis, argument, side equal 1. Well, there's 4 sides to these plots here, and it just so happens side 1 corresponds to the bottom x-axis. And I want to put tick marks at a sequence of numbers from 0 to 4.5 by 0.5. So let me execute that, or I guess I already did, and you can see the corresponding result. That SEQ, or sequence function, this is actually a separate function. So if I copy that out and paste it at the command prompt, you can see it generates a sequence of numbers. So it's just a quick way to get a bunch of numbers. Then if I also want my minor axis tick marks, I can do side equal 1 at, now I want to go by 0.1, 0 to 4.5. Labels equal false, meaning I don't want any numbers or labels generated with it. And TCK stands for tick. How do I want this tick drawn? Notice I didn't specify that before. I just went with the default. Here, 0.01 means I want, see these little tick marks here? I want them drawn 1% up relative to the size of this plotting area here. If I did negative 0.01, that would draw the little tick marks outside. Are there any questions? Now, we will have a whole section on graphics after we get done with this regression section. What I'm just telling you here now is just some of the very basics so we can get going with some stuff. Okay, so that takes us to page 13. Let's now estimate a regression model. The ultimate goal with this problem, or with this data set, is to let high school GPA predict college GPA. Again, if you think of yourself in a college admissions office, you want to use a person's background to predict how well will they do at your university, and then use that information to decide should you admit them or not admit them. That was the ultimate goal in this data set that obviously I actually made up myself. And so one way to help make that judgment then is to estimate a simple linear regression model with this particular data set. So to do this then, you can use the LM function. LM stands for linear model. Then the first argument is formula. This is where you tell R, hey, what's my response variable? What's my explanatory variable, or covariate, or independent variable, whatever you want to call it. And I want my college GPA to be my response. So you can say this is where you put your Y. And then I want my high school GPA to be my explanatory variable, or X. To separate the response from the explanatory variable, we use not an equal sign, because notice how equals are actually being used. We use a tilde. This is actually somewhat common syntax in other statistical software packages too, to use a tilde. If I were to have, let's say, other explanatory variables, such as ACT score, then I could just simply use plus ACT. So plus doesn't mean add, it just means and I want this additional explanatory variable. And you keep on using pluses for every additional explanatory variable you want to include. Now notice in this formula argument, I did not specify where my data was. So you didn't see me use GPA $ college.gpa. You could do that, yes. You could do that, just like what we did with the plot function. However, with the LM function and many other functions like this where you're actually estimating a model, you have an argument called data. And that's where you can specify the name of your data frame. Okay, let me run some of this code here. So if you notice, I'm going to put the results into an object called mod.fit, for the lack of a better name. I could have called it something else if I wanted to. So mod.fit gets the results from LM. To get an initial impression what mod.fit actually gives you, you can just type mod.fit right there. And so what we see here is the beta hat 0 and the beta hat 1, the estimated y-intercept, the estimated slope for the simple linear regression model. Now you might be thinking, geez, R doesn't really do much here. It just gives you beta hat 0 and beta hat 1. That's it. Actually, it gives you a lot more. It's just, unlike other software packages like SAS, you have to actually ask R to provide more information. And so there's going to be a couple times here today that are going to be, where I'm going to tell you, this is very, very important to understanding how R works in general. This is going to be one of those times. So to see then what actually is inside mod.fit, I use a function called names. Names mod.fit. Now I have the names of the items that are actually stored inside of mod.fit. To access something called coefficients, I type mod.fit $coefficients. To access residuals, I type mod.fit $residuals. To access the fitted values, in other words, the y hats, I type mod.fit $fitted values. So that's how you extract this information. Hopefully you see some similarities to what we were doing with the GPA data frame. We would say GPA $HS.GPA. Okay. So continuing on, this important point here. This mod.fit in R's terminology is what's called a list. L-I-S-T. To act and these coefficients, residuals, effects, all that stuff, those are components of the list. It's important that you know the terminology. The components of the list. That data frame that we saw before for GPA, that was also a list as well, but just a special kind of list. I'll explain more about that in about a minute or two. So, what a list provides you in R is a general way that you can store information of a variety of different types. Notice, for example, with the coefficients component, it had 2 things in it. The residuals component had 20 different things in it. There was 20 observations. So you can think of then the list as like this. Mod.fit, and then you link certain things to it, such as the coefficients, such as the residuals, such as the fitted values. And then, you can put a $sign on top of each of these arrows to indicate, well, this is how I pull that information out of the list. Now, as I mentioned to you before, GPA is the list too. It has high school.GPA. It has college.GPA. But it's a special kind of list called a data frame. The reason why it's a special kind is because notice college GPA and high school GPA all have exactly the same length. 20 observations, or 20 values. So a data frame is a special case of a list. Just to give you an idea of also how different the components of the list could be. So for example, there's one component called call. So if I do mod.fit $call, oh, look at that. I have my code back that was used to estimate the model. Very good for the reproducibility of research. But notice how that's completely different from these numerical values that we're getting before, like with mod.fit $fitted values. So a list is a way to store information. Many, many, many functions in R will return the results to you in this list format. Pretty much all model fitting functions, not just simple linear regression, but well, I won't go into all of them. they return the results to you in a list format because there's a variety of different things that you want back from fitting a model. They're not all the same type, and so it's a very useful data, I should call it data, it's a useful information storage tool. Okay, are there any, here's one other thing I want to show you. So, again, names, mod.fit, we got that. Also, names GPA. Remember how we had that as well from last time. But I want to know a little bit more about this LM function. So let's go into the help for it. So I'm going to do the HTML help this time. I could have just simply typed help parentheses LM and parentheses. I'm going to go the long way. So packages, LM is in the stats package. And let's click on L. There's LM right there. And so, this gives you the full syntax that one could use with the LM function. Obviously, we didn't use all the corresponding arguments. But notice here, everything's nicely listed as, here are the arguments in the description. I want to page down. Value. So, notice what's returned. A list containing at least the following components. Coefficients, residuals, fitted values. So, all the stuff that we saw from doing the names command are described to you in the help so that you know what that is. Very useful tool. Okay. Are there any questions? Yes.
So the values over here basically gives all the analysis part, like all the output that.
Like in SAS, a lot of this output would be automatically printed to your screen.
Yeah.
That doesn't happen here with one. And you have to extract it yourself. Any other questions? Okay, well, let's organize some of this stuff in a useful form. So, for example, let's create a data set, a new data set in R that has the data, but also has all the y-hats, the predicted values, and also the residuals. Common thing that you want to do. Excuse me. So how can I do that? Copy and paste some code over here. Okay. Well, I'm going to create a new data frame for this purpose. I'm going to call it save.fit for the lack of a better name. So save.fit gets the results from, to create a data frame, you use the function called data.frame. Then, inside the data frame, basically what I'm going to do is concatenate sets of information together by columns. So first to begin here, I have my GPA data set. There's 2 columns of information there. And then I'm going to create a new column of information called college.gpa.hat. Excuse me. So that's going to contain my y-hats. And remember how I extracted those y-hats before? mod.fit $values. But I'm going to do it in a nice way. I'm going to actually use a function called round with it to 2 decimal places. So if you really wanted to see, well, what's going to happen with that before you put all this stuff together, just copy and paste it out. And there you go. Those are my y-hats, rounded to 2 decimal places. Also up here, I'm going to create another column in my data set, or you can say a variable called residuals, and I'm going to round to 2 decimal places, mod.fit $residuals. Again, I put that all in an object called save.fit. And let's look at the first 6 values by using the head function. So I say head save.fit, and there you go. So the first observation, high school GPA 3.04, college GPA 3.1. What was the predicted college GPA from this model? 2.95. So it was a little off. How much was it off? 5.15. There you go. So again, here's all the information that's stored in mod.fit. You might want to now think, well, is there any way I can summarize all that information? Yeah, you can. How about we use the summary function? So many statistical software packages will essentially give this stuff to you automatically when you run the corresponding procedure or function or whatever code it is. And there's a summary of the information that's in mod.fit. Let me actually go over here to my notes so I can write on this easily. Oops, too far. So for example, right here is my beta hat 1, the estimated slope coefficient. Here is the square root of the variance, or the estimated variance of beta hat 1. How do I know that? It's in the standard error column. Unfortunately, things just got cut off there by the page break. 4.95 here is my t-test statistic. The test is beta 1 equal to 0 or not. And then the p-value is 0.0001. And in case you don't know that that is significant, there's 3 asterisks right next to it with significance codes. I don't know why that's there, but it is. The R squared coefficient of determination is 0.577. So there's a nice summary of information there. And do any of you remember from last time us using the summary function as well? Hopefully the answer is yes. So remember last time we did summary parentheses GPA. So notice the exact same function. But wow, look at that. I get a different result coming back to me. I'll explain why that occurs shortly. That will be the second really big thing to understand about how R works to get out of our lecture today. Okay. So what I've done here in the notes is then I've actually written out the model. Of course, you could use Y's, you can use X's for the response and explanatory variable. Just, of course, make sure you explain what Y is, what X is. Or you could actually just simply use words as well when you write out your estimated model. Always, it's important to make sure to include some kind of hat on top of your response there, because now we're talking about the predicted value rather than the actual value. Okay, well, what if we have a categorical explanatory variable? For those of you who've taken Stat 820 or are taking Stat 821, have you talked about categorical explanatory variables in a regression model context? Like, how do you include these categorical variables that are maybe coded with words? How do you include them in a model? You might have seen it in other courses, but have you talked about it in 821? So let's say if you have a factor with treatment levels, do you know how to, what does your X matrix look like? Have you talked about that? Your design matrix? Is that a yes? I'm going to have to talk to Walter through it. Anyway. Okay. Well, let's suppose that we have another variable in the data set. So I need to actually add a variable. And this variable is simply going to correspond to, for their undergrad, for their time in college, did they live with their parents? Did they live in a dorm? Did they live off campus? I'm just making something up so that we have a categorical explanatory variable. It has 3 levels to it. So to somehow get this into my data frame, this is what I'm going to do. Copy some code over first. Okay. So I'm going to combine together, remember the C function that we've seen before, which actually in R's terminology stands for concatenate. Combine together 3 words or phrases with parents, dorm, and off campus. And then I'm going to, because I need basically, I want to have 20 of them. I want to have 20 of these observations, you could say, so I can put them nicely into my data frame. So what I'm going to do is repeat, using the REP function, the information that's in where.live, each of them 7 times. So when I put that into X, this is what I get. I have 21 observations. Again, I only need 20. So then when I put this in my data frame with GPA, I create an object using data.frame, GPA, and then I'm going to create a new variable called where.live in that data frame. And I'm going to say x bracket minus 21 end bracket. Does anyone remember what minus does? It basically removes that 21st observation in this case. So now where.live is exactly the same length, or I'm sorry, it's the same number, well, what we will want in the same number of rows as GPA does. And so that when I put this into a new object called GPA3, and take a look at it, we can see that indeed we do have our data set. We can look at it all. It's not that big. Okay. So next, what I would like to do is examine, well, how does R treat the fact that this where.live is actually a categorical variable? And to do that then, I'm going to use a function called levels. So levels parentheses GPA3 where.live. Okay, so this then begins page 17. So R has, in R's terminology, again, this is you have to learn R's terminology. R's terminology, this where.live that's in GPA3 is what's called a factor. So you've seen in probably many other classes, or at least one class before, factors in a statistical context is like or in an experimental design context is something that contains various treatment levels. And those are categorical levels, essentially. And so by using the function levels, I can see the levels, or the treatment levels, of this factor. Now, I would like to figure out, well, how will R actually include then this factor in a regression model? So to see how R is going to do this, I can use the function called contrast with it. And this gives me how R is going to treat this factor, because everything has to be converted to numbers. You can't add, let's say, dorm to off-campus. You could add 0 to 1. So you have to transform everything into a numerical format. And this tells me how this numerical format is going to be done using what are often referred to as indicator variables. Some people might use the terminology dummy variables. So here we have a table. We have the 3 levels of where to live. Let me actually go over here so I can write on this. And let's just call this for now x1 and x2. R is going to create 2 indicator variables to represent the 3 levels of where.live. Why does it need 2 versus 3? Well, hopefully you've seen this in another class, and that is because every level is going to be represented uniquely. So, for example, x2 corresponds to either you're with your parents or not. So in any observation that has with your parents, you assign a value of 1. For any observation that is not with parents, like dorm or off campus, you assign a value of 0. That's your indicator variable to represent this categorical level in a regression model. In a similar manner, off campus is a 1 for any observation that has off campus, 0 otherwise for this x1 indicator variable. Rather than calling these x1 and x2, R simply uses the terminology instead. Where's my eraser? There it is. X1 is going to be off campus because it's an indicator representing off campus or not, for example. Now also notice how dorm is all zeros. Why? Well, because now every level of that categorical explanatory variable has a unique coding to it. So it will be represented uniquely in the model. If you, for some reason, have not seen that before, I think this will be even more clear once we actually look at the corresponding regression model. So the reason why we did the levels there, and perhaps I didn't explain that part well, is so that I had some idea of how R's ordering the levels. Because R will always put that first level, however it's ordered, as the all zero level, you can say, or the base level, if you've heard that terminology before. Always will put that first level as the base level. By default, R always puts everything in alphabetical order. You can get that changed, but by default, that's how it's done. SAS does something very similar, but there's a big difference. Rather than using the set first level equal to all zeros, SAS does set the last level to be all zeros. So in SAS, it would do something like this. Okay? Hopefully, for those of you who are taking Set 821, you've seen something like this, maybe just not written out like this. So when you construct that X matrix, that design matrix, this is how it's done with all the zeros and ones. Okay, so then when we estimate the model, notice I'm including an extra variable in there. I put the results in mod.fit3. I summarize the information. Look how R does this. We have two indicator variables that have corresponding beta hats with them. Look at how R uses it in terms of its labeling. It uses the name of the categorical variable, where.live, and then it puts the corresponding indicator variable name right next to it. So that then, if we actually write out the actual model, there you go. Now, as again, a further way to understand, well, why are there only two indicator variables for a three-level categorical variable? What you can do on your own is write out the model, supposing you have dorm. Write out the model, supposing you have off-campus. Write out the model, supposing that you have parents. So you have three different written out models where you're just coding in the actual explanatory variable value for where.live. You see that then you actually have three different models. So indeed, the model does truly represent the three levels that you have for that categorical explanatory variable with only two indicator variables. Okay. Now there are times when you're on an R and that you will have a data set where the categorical explanatory variable has a numerical coding to it. So maybe instead of using those words for where.live, maybe I simply use 1, 2, or 3. But we don't want R to recognize that 3 is greater than 1 because it's not. They're just labels to represent the three levels, such as dorm, off-campus, or parents. And so to tell R, hey, treat this as a categorical explanatory variable, use the factor function. Say, hey, this is actually a factor, not a numerical variable. It's actually a factor. And you do that in your model specification. Or at least that's one place to do it. And so I give some information about that a little bit more in my program. Please take a look at that. Well, what happens if you have a situation where, now this is getting away from the formula, getting away from factors. And we're going to go to about, well, what will be on that clock, about 127, 128. It's actually 120 right now, since we started about 5 minutes late. Now, what if, now with that high school GPA, maybe you also want a high school GPA squared in the model. How can you do that? Well, here's a formula argument that shows how. As you might expect, hs.gpa caret sign 2. But notice I'm using a function simply that's the I function around it. That's kind of strange. I'll explain more why that's coming up after this next example. Let's say also you are interested in a model that has an interaction term. So let's say you have x1, x2, and you want x1 times x2 in a model. How can you tell R that in a formula argument? Well, simply x1 plus x2, x1 colon x2. That's how you do the interaction. So x1 times x2 is x1 colon x2 in the syntax. Now you could, so you probably thought, well, why didn't you do this? x1 asterisk x2. You could. But in R's or in R's syntax, this basically means you want x1 and x2, the main effects, along with the interaction. Okay? Then there's one more way that you could actually represent this model too. You could say parentheses x1 plus x2 and parentheses caret sign 2. What that's telling R is that anything inside that parentheses, you want the main effects and all the way up to the two-way interactions. Now hopefully you see what the problem is if I were to only put hs.gpa caret sign 2 there. And that is in our syntax, that caret sign 2 doesn't mean squared in a formula argument. It still means squared there, like at a command prompt. It's just only in a formula argument itself. That caret sign 2 or even caret sign 3 doesn't mean what you think, or at least it would mean what you think initially. Instead, it corresponds to the interactions. How high of a model in terms of orders of interactions do you want to go? Do I want to do two-way? Do I want to go up to three-way interactions, and so on? So to tell R that indeed I do want a squared term in there, the I function says, okay, treat this as you would normally expect as high school GPA squared. That's all. Look at the help for I. It's kind of a weird way that they word that. Treat this as you would normally expect in a formula argument. So those are some of the basic ways in terms of various model terms that one would have in a formula argument that are very fundamental to using R. It can be frustrating if you simply don't know, okay, caret sign 2, why isn't this giving me a square term? Okay. Then this leads us then to what I had mentioned earlier about the summary function. How summary actually acted two different ways depending upon, well, what object I have in there. And this comes down to one of the most important concepts to understand with R. R is often referred to as an object-oriented language, meaning depending upon the object type, like an object that is a data frame, or an object that is coming from, let's say, the LM function, depending upon the object type, some functions may change how they work. Okay? Summary is one of them. So every object in R has what's called a class to it. So for example, the class of GPA just so happens to be data.frame. The class of mod.fit just so happens to be LM. There are ways inside the function where you declare classes. The class of LM, remember that's an actual function. It just so happens the class happens to be called a function. the class of the high school GPA that was inside of the GPA data frame is numeric. This is just a bunch of numbers. And so there are functions in R, and notice how I get the class. I just issued the class function. So there are functions in R that are called generic. What that means is that they can work with a variety of objects that have different class types. They can work with data.frames. They can work with LMs. And the way that these functions work is this. We'll take the example of summary, and then we'll end it for today. When I issue the command summary mod.fit, the first thing that R does, it finds the class for mod.fit. So it will do that in this particular case and say, oh, that's a class of LM. And then what it will do is try to find another function. That function is this, the generic function name dot, what is the class of that object, LM. And so, look what happens then when I issue summary.lm mod.fit. I get exactly the same result. In a similar manner, with the GPA, excuse me, the first thing that R is going to do is look for summary, it's going to look for the class for GPA. That class is data.frame. Then it's going to try to find a function called summary.data.frame. And you get exactly the same result. Summary.lm, summary.data.frame are referred to as method functions. So you have generic functions, and then you have method functions. This can be one of the more confusing aspects for people who are just first learning how to use R. But it's a very fundamental concept to understand, and obviously we're out of time here, and I will start talking about this again next Tuesday. This is extremely, extremely important. If you come out of this class not understanding why R is an object-oriented language, meaning depending upon the class of the object, a certain reaction will happen with generic functions. If you come out of this class without knowing that, I have failed. Are there any questions? Okay, and that's it for today.